Number 1. The Great Oxidation Event. 2.4 billion years ago, the most counterintuitive killer in Earth's history was already at work. Not a volcano, not an asteroid, not a glacier. Oxygen. The same gas keeping you alive right now. To understand what happened, you have to forget almost everything you know about Earth. There were no plants, no animals, no fungi, no fish. The continents themselves were strange, smaller, half-formed assemblages of rock drifting across a planet whose seas were green from dissolved iron, and whose skies glowed with a thick orange haze of methane. Life existed, but it was microbial. It was anaerobic. It had ruled the planet uncontested for at least 1.5 billion years. Methanogens, sulfate reducers, fermenters. These were the dominant kingdoms of life on Earth, and every single one of them shared one trait. Oxygen, to them, was a poison. The trouble began with a group of bacteria called cyanobacteria. They had evolved a new chemistry around 3 billion years ago, possibly earlier. They could split water molecules using sunlight and produce free oxygen as a waste product. Photosynthesis. For 300 million years, maybe longer, cyanobacteria pumped oxygen into the world's seas, and almost nothing happened, because the oceans were saturated with dissolved iron, gushing endlessly from hydrothermal vents along mid-ocean ridges. Every oxygen molecule the cyanobacteria released bonded immediately with iron, forming insoluble iron oxides that drifted to the seafloor. The Earth was rusting. We can read this rusting today in geological structures called banded iron formations, the Hamersley Basin in Western Australia, the Transvaal Basin in South Africa, layers of red iron oxide alternating with darker silica, deposited slowly across hundreds of millions of years. These formations contain roughly 600 billion tons of iron, which is around 90% of the iron ore currently mined on Earth. Every car, every skyscraper, every steel beam traces back to the GOE. But the iron ran out. Once the dissolved iron was exhausted, cyanobacterial oxygen had nowhere to go. It started accumulating, first in the ocean, then in the atmosphere. Atmospheric oxygen rose from less than 0.1% of present levels to between 1 and 10% of present levels, somewhere between 2.45 and 2.32 billion years ago. The signature of this rise is preserved in something called mass-independent fractionation of sulfur isotopes, or SMIF. James Farquhar discovered in 2000 that SMIF signals abruptly disappear in rocks younger than 2.4 billion years. That disappearance marks the moment Earth's atmosphere became oxygenated, and for the anaerobic life that had ruled the planet, oxygen was lethal. Free oxygen generates reactive oxygen species. Superoxide, hydrogen peroxide, hydroxyl radicals. These molecules tear cellular machinery apart at the chemical level. Modern aerobic organisms, including us, defend against them with enzymes like catalase, superoxide dismutase, and peroxidase. The anaerobes had no such defenses, they had never needed them, and so they died, not all at once. The GOE was not a sudden cataclysm, but a slow strangulation lasting hundreds of millions of years. We do not have body fossils to count the dead, but we know from geochemistry that an enormous proportion of Earth's microbial biomass was eliminated. The survivors retreated to the only places oxygen could not reach: deep ocean sediments, anoxic lake bottoms, hydrothermal vent systems, the guts of animals that did not yet exist, and then the climate collapsed. Atmospheric oxygen reacted with methane, breaking it down into carbon dioxide and water. Methane had been the dominant greenhouse gas, far more potent than carbon dioxide. When it disappeared, Earth's greenhouse effect crashed. The Hirnantian glaciation began. It would last roughly 300 million years, one of the longest ice ages in Earth's history. Glacial deposits in the Gaugonda Formation in Ontario, Canada, suggest ice may have extended to the equator, a snowball Earth. Heinrich Holland laid the foundations of GOE research in the 1990s. Donald Canfield, Lee Kump, and Timothy Lyons refined the timeline through the following decades. Joseph Kirschvink at Caltech and Andre Becker at UC Riverside have proposed that the breakup of the supercontinent Knorrland may have catalyzed the event by exposing fresh continental shelves to weathering. The GOE eventually paved the way for everything that came after. Mitochondria, the powerhouses of complex cells, are descended from aerobic alpha proteobacteria engulfed by anaerobic archaea after oxygen became available. The first eukaryotic fossils, the Francevillian biota of Gabon, appear roughly 2.1 billion years ago just after the oxygenation. Life had killed itself by accident, and in doing so, made everything else possible. But the ocean had killed once, it would kill again, and the next time, complex life would be the target. Number 2. The End Triassic Extinction. 201.564 million years ago, with an uncertainty of only 15,000 years, the Triassic-Jurassic boundary marks one of the most precisely dated mass extinctions in Earth's history. The dating comes from work by Blackburn and colleagues in 2013 using uranium lead zircon geochronology. The world they describe was nothing like ours. Land was dominated by therapsids, synapsids, and the early dinosaurs. The seas teemed with ammonoids, with conodont eels, with the first scleractinian corals building reefs that wrapped around the supercontinent Pangaea. And then, in geological terms, almost overnight, half of marine genera and roughly 80% of all species were gone. The conodonts, eel-like jawless creatures whose tooth-shaped microfossils had anchored 300 million years of stratigraphy, went completely extinct. Conularids, an extinct group of cnidarians, vanished. Most ammonoids, except the ceratitids, disappeared. Brachiopods, bivalves, the last placodonts, most ichthyosaurs, all suffered devastating losses. Reef ecosystems collapsed almost completely. Scleractinian corals, which had only emerged in the Middle Triassic, lost 96% of their genera. The kill mechanism was the Central Atlantic Magmatic Province, known as CAMP. It was one of the largest large igneous provinces in Earth's history. Camp basalts covered roughly 11 million square kilometers across what is now eastern North America, northwestern Africa, and northeastern South America. The total volume of magma erupted exceeded 3 million cubic kilometers in pulses lasting roughly 600,000 years. You can still see camp today. The Palisades Sill on the Hudson River near New York is a camp intrusion. The basalts of the Newark Basin are camp lavas. Most of these formations are now buried under sediments, but their geochemical signature is unmistakable. Camp did not just erupt lava. It outgassed an estimated 100,000 gigatons of carbon dioxide, plus enormous amounts of sulfur dioxide, methane, and toxic halocarbons released when magmas intruded into Triassic coals and evaporates. Atmospheric carbon dioxide rose from roughly 1,000 parts per million to potentially over 4,400 parts per million. Global temperatures rose by 4 to 6 degrees Celsius, and the oceans paid the price. Ocean acidification was severe enough to drop seawater pH by an estimated 0.3 to 0.5 units. That is comparable to projections for end of 21st century anthropogenic acidification. What happened in the seas is technically called a calcification crisis. Aragonitic shell builders, including corals, certain ammonoids, and some bivalves, dissolved preferentially over those with calcite shells. This pattern, documented by Mike Benton at the University of Bristol and Paul Wignall at the University of Leeds, is one of the clearest signatures of acidification in the geological record. Massive ocean anoxia developed in many marine basins. We know this from black shale deposits and from excursions in molybdenum, uranium, and rhenium isotopes that geochemists use as paleoredox proxies, which means proxies for ancient oxygen levels. The St. Audrey's Bay section in Somerset, England, provides one of the most complete stratigraphic records of the boundary anywhere on Earth. Walking that cliff face today, you can see the carbon isotope signature of the extinction directly in the rock, a negative excursion in delta-13 carbon of 2 to 6 per mil. That isotopic shift records the massive injection of light carbon, almost certainly from volcanic carbon dioxide and methane combined. Some researchers, including Manfredo Capriolo, argue for a methane hydrate destabilization positive feedback. The hypothesis is that initial camp warming destabilized methane stored in seafloor sediments, which then released and amplified the warming. Other researchers, including Jessica Whiteside and Paul Olson, have shown that the extinction was probably not a single instant but a multi-pulse pattern, occurring over 600,000 years aligned with successive camp eruptions. The aftermath reorganized terrestrial life. With the dominant therapsids and many large reptiles cleared away, dinosaurs, which had evolved in the Triassic but remained ecologically minor, exploded into the niches left empty. Pterosaurs diversified. The Jurassic Age of dinosaurs would not have happened without the End Triassic killing field. But the End Triassic was not the worst. It was not even the most surprising. To find an extinction that defied the pattern entirely, we have to go further back in time to a moment when the ocean did not burn. It froze. Number 3. The End Ordovician Hirnantian Glaciation. 445 million years ago, the second largest mass extinction in Earth's history began as the planet suddenly entered an ice age. To grasp what was at stake, you have to remember that almost all complex life at this point lived in the sea. Land hosted only microbial crusts, primitive bryophytes, and possibly the earliest arthropod colonizers. Trilobites scuttled across continental shelves, graptolites, planktonic colonial hemichordates drifted through the open ocean, brachiopods, bryozoans, conodonts, and the last of the eurypterids, the giant sea scorpions, dominated marine ecosystems. The End Ordovician extinction eliminated roughly 85% of marine species. Because almost all complex life was marine, this was effectively a near extinction of all complex life on Earth. What makes the End Ordovician unique is that it killed in two distinct pulses. The first pulse occurred at the Hirnantian glacial maximum, roughly 445 million years ago. The supercontinent Gondwana, which then sat over the South Pole, accumulated an enormous ice sheet. That ice sheet covered at least 6 million square kilometers. We can still see its traces today in glacial striations and tillites, preserved in present-day Algeria, Libya, and Mauritania. As ice locked up seawater, global sea levels dropped by between 70 and 100 meters. The continental shelves where most marine biodiversity lived were exposed and dried. The cool water Hirnantia fauna, a brachiopod and trilobite assemblage, replaced tropical marine communities globally during this glacial maximum, a pattern documented by paleontologists Christian Rasmussen and David Harper. Graptolites, particularly diverse and abundant before the extinction, lost roughly 70% of their species. Trilobites suffered enormously, the first pulse killed by cold and habitat loss. But the second pulse killed by warmth. Roughly 2 million years later, around 443 million years ago, the Gondwanan ice sheet melted rapidly. Sea levels surged back, flooding the previously exposed continental shelves with water that was warm, expanding, and severely depleted of oxygen. This deglacial anoxic phase is recorded globally in widespread black shale deposits. The early Silurian hot shale interval that formed during this anoxia became one of the world's most important hydrocarbon source rocks. Most of the oil currently produced in North Africa and the Middle East comes from organic carbon buried during the End Ordovician deglacial anoxia. Iron speciation and uranium isotope studies by Stephanie Bates, Tianchen He, and Eric Sperling have documented widespread euxenia during this second pulse. Euxenia is a particular kind of anoxia where the oxygen-depleted water also contains dissolved hydrogen sulfide, which is acutely toxic to most marine animals. Recent research in the 2020s, led by John Marshall at the University of Southampton, has implicated severe ozone layer destruction from intense ultraviolet radiation as an additional kill mechanism. The hypothesis suggests that mercury and halogen released during volcanism damage the ozone layer, allowing ultraviolet radiation to reach the surface and amplify the extinction. The Hirnantian carbon isotope excursion, called the HICE, is a sharp positive shift in delta-13 carbon of 3 to 4 per mil that marks the glacial peak. It reflects massive organic carbon burial during the cold phase. The cause of the glaciation itself remains debated. Leading hypotheses include drawdown of atmospheric carbon dioxide from continental weathering, particularly weathering of the newly emerged Appalachian and Caledonian mountain ranges, and possibly volcanic-induced cooling from large-scale eruptions. Sea surface temperature drops of approximately 5 degrees Celsius have been documented through oxygen isotopes from conodont fossils. Seth Finnegan at UC Berkeley has argued that the extinction severity stemmed from the combination of rapid temperature change, oxygen depletion, and habitat loss, rather than any single cause. The Wangjiawan section in Hubei Province, China, is the global stratotype section endpoint that defines the base of the Hirnantian stage. The End Ordovician is unique among the Big Five because of its dual-direction kill mechanism. Cold killed some lineages, warming and anoxia killed others. Most other mass extinctions are single-direction climate events, and despite its severity, the End Ordovician had relatively minor long-term ecological consequences. Most major taxonomic groups recovered their pre-extinction ecological roles within a few million years. The Silurian seas that followed looked in many respects like the Ordovician seas they had replaced. But the next extinction was different. The next time the ocean turned on its inhabitants, the killer would not be ice or fire. It would be life itself, on land. Number 4. The Late Devonian Hangenberg and Kellwasser events. Between 372 and 359 million years ago, the planet experienced two distinct extinction pulses that together eliminated roughly 75% of marine species. The Kellwasser event marks the Hirnantian-Famennian boundary, around 372 million years ago. The Hangenberg event marks the Devonian Carboniferous boundary, around 359 million years ago. The two events take their names from rock units in Germany. The Kellwasser kalk is a black limestone in the Harz Mountains, first studied systematically by Walter Bugisch and other German paleontologists. The Hangenberg shale is a black shale in the Rhenish Slate Mountains. Both events left behind organic-rich black shales globally, which is the geological signature of widespread ocean anoxia. The Kellwasser event devastated reef builders, stromatoporoid sponges, and tabulate corals, which had built the largest reef systems in Earth history during the Devonian, never recovered to their pre-extinction prominence. Trilobites suffered catastrophically. The Phocapida and Proetida orders lost most of their diversity. Only one trilobite order would survive past the Permian. Placoderms, the armored fish that dominated Devonian seas, went completely extinct at the Hangenberg. The most famous placoderm, Dunkleosteus torelli, reached 6 meters in length and possessed a bite force estimated at 5,300 newtons at the tip of its bony jaw and 7,400 newtons at the back. It was one of the most powerful predators ever to evolve. It vanished forever. Conodonts, ammonoids, and brachiopods all suffered major losses across both pulses. The Hangenberg uniquely affected early tetrapods, the first land-dwelling vertebrates. Lawrence Salon and Michael Coates demonstrated in 2010 that the Hangenberg created what paleontologists call Roemer's gap. This is a 15 million year interval after the extinction with almost no fossil tetrapods. The lineages that had crawled onto land in the Devonian were nearly wiped out by an extinction whose primary cause was in the oceans. The proximate cause of the anoxia was massive eutrophication. Eutrophication means nutrient overloading. Nutrient runoff into the oceans triggered enormous algal blooms whose decay consumed all available oxygen, but the ultimate cause is the most extraordinary in the entire history of mass extinctions. The ultimate cause was the rapid evolution of vascular land plants in the first true forests. During the Devonian, plants like Archaeopteris evolved. Archaeopteris was the first modern-style tree with a true trunk and a true root system, reaching heights of around 30 meters. Its deep root systems aggressively weathered rocks, breaking them down chemically and releasing phosphorus, nitrogen, and other nutrients into rivers and ultimately into the oceans. This is the only mass extinction in Earth's history thought to be caused by the evolution of new life on land triggering ocean collapse, a biotic cause rather than a purely geological or astronomical one. Atmospheric carbon dioxide may have crashed from around 4,000 parts per million to around 400 parts per million during the Devonian as forests sequestered carbon, contributing to climate cooling. A brief but severe Famennian-Tournaisian glaciation occurred during the Hangenberg, supported by glacial diamictites preserved in northern Brazil, studied by Daniel Lacan and others. Mercury anomalies in Kellwasser and Hangenberg sediments, documented by David Bond and Stephen Grasby, also implicate volcanic eruptions. The leading suspect is the Pripyat-Dnieper-Donets large igneous province, which lies in present-day Ukraine. The volcanic role appears to have been secondary to the biotic forcing. There is also a more controversial hypothesis. Marina Rakotinsky and colleagues have proposed an extraterrestrial trigger for the Hirnantian-Famennian event, citing iridium and possibly platinum group element anomalies in boundary sediments. The hypothesis remains contested. The Alamo Breccia in Nevada represents an impact deposit dated to roughly 382 million years ago, but its connection to the Kellwasser event is unclear. John Marshall, the same University of Southampton researcher who proposed the End Ordovician ozone destruction hypothesis, has argued, based on malformed plant spores from the boundary, that ozone layer destruction from ultraviolet radiation contributed to the Hangenberg extinction. The Koala Quarry section in Poland's Holy Cross Mountains is one of the most studied Hangenberg sections, providing a near-continuous record of the boundary. The Devonian extinctions teach a sobering lesson. Even the slow, beneficial spread of forests across continents, the same forests that would eventually shade and shelter the ancestors of mammals, was capable of destabilizing the entire ocean. But the Devonian extinctions, devastating as they were, did not approach the scale of what came next. To find the worst extinction in Earth's history, we have to travel forward in time another 100 million years. Number 5. The End Permian Great Dying. 251.941 million years ago, with an uncertainty of only 37,000 years, the most severe extinction event in Earth's history began. The dating, by Burgess, Bowring, and Shen in 2014, used high-precision uranium-lead zircon geochronology. The numbers alone are staggering. 96% of marine species, 70% of terrestrial vertebrate species. Most of this devastation occurred within 60,000 years or less. Some estimates suggest the main extinction pulse may have unfolded in as little as a few thousand years. To put this in perspective, 60,000 years is roughly the same amount of time anatomically modern humans have existed outside Africa. The driver was the Siberian Traps eruption, the largest continental flood basalt province in Earth's history. The Siberian Traps covered roughly 7 million square kilometers of present-day Siberia, with an estimated total magma volume of 4 million cubic kilometers. The eruption released approximately 100,000 gigatons of carbon dioxide, plus massive amounts of sulfur dioxide, hydrogen chloride, hydrogen fluoride, and methyl chloride. But the worst part of the Siberian Traps was not the lava itself. It was what the magma encountered as it ascended. The Tunguska Basin, where most of the Siberian Traps emerged, contained vast deposits of coal and salt. When Siberian magmas intruded into these deposits, they baked them, releasing additional gigatons of greenhouse gases and toxic halocarbons. Henrik Svensson at the University of Oslo has documented these intrusions and the strange volcanic structures, called diatremes, that they created. Tropical sea surface temperatures during the End Permian reached approximately 40 degrees Celsius. That is lethal for most marine animals. Global temperatures rose by 8 to 10 degrees Celsius in the tropics. Severe ocean acidification dropped seawater pH by between 0.6 and 0.7 units. Aragonitic and high magnesium calcitic organisms, including all the surviving rugose and tabulate corals, suffered preferentially. Their shells dissolved in the acidified water. Near global ocean, anoxia developed, evidenced by widespread black shales, framboidal pyrite distributions documented by Paul Wignall, and excursions in uranium and molybdenum isotopes. Hydrogen sulfide poisoning extended into the photic zone, the sunlit upper layers of the ocean. We know this from green sulfur bacteria biomarkers, specifically isoran near autane derivatives. Green sulfur bacteria require both light and dissolved hydrogen sulfide. Their presence in shallow water sediments is direct evidence that sulfide had risen from the deep sea into the surface ocean. Lee Kump and colleagues proposed in 2005 that hydrogen sulfide could have escaped from the oceans into the atmosphere, killing terrestrial life and damaging the ozone layer. Henk Vischer subsequently found malformed gymnosperm pollen grains at the boundary, evidence of mutation potentially caused by ultraviolet B exposure following ozone collapse. The roll call of victims is the longest in Earth's history. Trilobites, survivors of every previous extinction since the Cambrian, with 290 million years of existence behind them, went completely extinct. Eurypterids, the giant sea scorpions, vanished. Tabulate and rugose corals were eliminated. Producted brachiopods, blastoid echinoderms, fusulinid foraminiferae, all the trilobites, and most ammonoids disappeared from the geological record permanently. On land, the dominant therapsid synapsids, the proto-mammals that had ruled Permian continents, were nearly wiped out. Only a few lineages, including the ancestors of Lystrosaurus, survived to dominate the bleak early Triassic. The Mishan section in Zhejiang Province, China, is the global stratotype section and point for the Permian-Triassic boundary, and it is one of the most intensively studied stratigraphic sections in geology. A negative delta 13 carbon excursion of 5 to 7 per mil at the boundary indicates massive injection of isotopically light carbon, consistent with combined volcanic carbon dioxide and methane release. Recovery from the End Permian was extraordinarily slow. Full ecological complexity in marine ecosystems was not restored until the Middle Triassic, between 5 and 10 million years after the extinction. There is a feature of the early Triassic geological record called the coal gap. For 10 million years following the End Permian, there is a complete absence of coal deposits anywhere on Earth. The terrestrial peat-forming ecosystems that produce coal had been so thoroughly destroyed that no significant peat accumulation occurred for 10 million years. Microbial reefs replaced metazoan reefs in the early Triassic, indicating a fundamental ecological reorganization. The animal-built reef ecosystems we associate with healthy modern oceans were absent. There are competing theories about the precise mechanism of the End Permian. The mainstream view is that Siberian traps emissions of carbon dioxide and sulfur dioxide were the primary trigger. A second view emphasizes methane hydrate destabilization as a positive feedback amplifier. A more controversial view proposed by Becker and colleagues in 2004 argues for an extraterrestrial impact at the Bedout High structure off northwestern Australia. This impact hypothesis has been largely rejected by the scientific community. The End Permian represents the most extreme example in Earth's history of a carbon-driven extinction. It is regularly cited as a worst-case scenario for current anthropogenic climate change. There is one critical comparison worth making. Present-day rates of carbon dioxide emissions are approximately 10 times faster than even the Siberian traps emissions during the End Permian. The End Permian unfolded over tens of thousands of years. We are running its experiment over decades. But there is one more extinction left to consider. The most famous one. The one everyone has heard of. And in this video, the ocean's role in it has been almost entirely overlooked. Number 6. The End Cretaceous KPG extinction. 66.043 million years ago, an asteroid struck the Yucatan Peninsula. The impact killed roughly 75% of all species, including all non-avian dinosaurs, all pterosaurs, all mosasaurs, all plesiosaurs, all ammonites, all rudous bivalves, and most planktonic foraminifera and coccolithophores. The dating, by Rene and colleagues in 2013, combined argon-argon and uranium lead techniques to pin the boundary down to within 43,000 years. The asteroid hypothesis was first proposed in 1980 by Luis and Walter Alvarez, Frank Asaro, and Helen Michel. They had discovered a global iridium anomaly at the Cretaceous-Paleogene boundary, a layer of clay enriched in iridium hundreds of times above background levels. Iridium is rare in Earth's crust, but abundant in certain types of asteroid. The Chicxulub crater itself was identified in 1990 by Alan Hildebrand and his collaborators. The crater sits beneath the Yucatan Peninsula in Mexico. It is approximately 180 kilometers in diameter. The impactor itself was estimated to be between 10 and 14 kilometers in diameter, striking at roughly 20 kilometers per second. The impact released energy equivalent to approximately 100 trillion tons of TNT. That is roughly 2 million times the energy of the largest hydrogen bomb ever detonated. In 2016, the International Ocean Discovery Program and the International Continental Scientific Drilling Program partnered on Expedition 364, led by Sean Gulick and Joanna Morgan. The expedition drilled into the peak ring of the Chicxulub crater. The cores recovered revealed the structural details of the impact and the hydrothermal aftermath that lasted for hundreds of thousands of years. But here's the part most people miss. The Chicxulub impact occurred in shallow seas. The target rock was not just basement granite, it was rich in sulfate evaporites. The impact vaporized those evaporites and injected massive amounts of sulfate aerosols into the stratosphere. The aerosols caused approximately 3 to 10 years of impact winter. Global temperatures dropped by an estimated 25 degrees Celsius. Sunlight reduced by 50% or more. Photosynthesis collapsed, but the aerosols did not stay aloft forever. As they rained out, They became sulfuric acid. Ocean acidification followed. A 2019 study by Michael Hirnantian and colleagues using boron isotopes in foraminifera fossils documented an ocean pH drop of approximately 0.25 units in the immediate aftermath. That was sufficient to crash carbonate-shelled plankton populations globally. What followed is sometimes called the Strangelove Ocean. Surface ocean primary productivity collapsed for hundreds of thousands of years. Phytoplankton, the base of the marine food web, died en masse. The entire food chain unraveled from the bottom up. Coccolithophores, single-celled algae that built the white chalk cliffs of Dover and Champagne, suffered approximately 93% extinction. The white chalk that had been deposited continuously through the late Cretaceous simply stops appearing in the geological record at the boundary. Planktonic foraminifera lost more than 90% of their species. Only a handful of small generalist species, including Gwembulitria cretacea, survived to repopulate the Paleogene oceans. Tsunamis from the impact reached estimated heights of 100 meters or more in the Gulf of Mexico. Tsunami deposits have been found across the Caribbean, across Mexico, and along the United States Gulf Coast. The KPG deposit at the Brazos River in Texas contains multiple stratigraphic layers reflecting backwash and Seiche oscillations that lasted weeks. A 2022 study by Mario Fischer-Gode used ruthenium isotopes to confirm that the Chicxulub impactor was a carbonaceous asteroid from the outer solar system, not a comet. Some scientists have argued that the Deccan Traps eruption in present-day India, which was ongoing during the KPG boundary, may have contributed to long-term ecological stress before and after the impact. Most evidence still points to the impact as the main extinction trigger. But the Deccan Traps may have weakened ecosystems enough to make the impact's effects worse than they would otherwise have been. Mosasaurus hoffmanni, the dominant marine reptile predator of the late Cretaceous, reached lengths of 17 meters. It was an apex ocean hunter. It was gone within months of the impact. Ammonites, which had survived multiple previous mass extinctions over 340 million years of existence, finally vanished at the KPG, although the heteromorph ammonites had been declining for millions of years before the boundary. The Tanis site in North Dakota, discovered by Robert De Palma, contains fish with Chicxulub impact spherules embedded in their gills. These fossils are direct physical evidence of the impact's effects within minutes to hours of the event. Here is the reframe that matters. The asteroid started the KPG extinction, but the ocean finished it. Acidification, plankton collapse, and tsunamis did the killing in the water. The asteroid was the trigger. The ocean was the executioner. And that pattern of the ocean as the actual killer runs through all 6 of the events we have just examined. What links these 6 catastrophes is not a coincidence. It is a pattern, a signature, a vulnerability that has expressed itself again and again across more than 2 billion years of Earth's history. The first link is rapid carbon injection into the atmosphere-ocean system. The Great Oxidation Event injected oxygen via photosynthesis. The End Triassic injected carbon dioxide via camp volcanism. The End Permian injected carbon dioxide via the Siberian traps. The Late Devonian injected nutrients via forest-mediated weathering. The KPG injected sulfate aerosols followed by carbon dioxide via impact and Deccan traps volcanism. In every case, a chemistry shock triggered the cascade. The second link is ocean chemistry crash. Whether through oxygen saturation, acidification, anoxia, or euxinia, the ocean's chemistry shifted beyond what life could tolerate. The third link is ecological collapse from the bottom up. Plankton and base of food web organisms were hit first. Coccolithophores, foraminiferae, photosynthetic bacteria, all critical primary producers, all repeatedly devastated. The fourth link is that reef ecosystems are the canaries. Devonian stromatoporoid reefs, Triassic scleractinian corals, Permian rugose and tabulate corals. All collapsed first, all recovered slowest. The fifth link is the recurring calcification crisis. Aragonitic shell builders die preferentially during acidification events. The signature appears in the End Triassic, the End Permian, and the KPG. The role of large igneous provinces is the most reliable extinction trigger in the geological record. Siberian traps, camp, Deccan traps. The hypothesized Pripyat Dnieper, Donetsk province in the Devonian. When the planet's interior breaches its surface on a continental scale, the oceans suffer first. There's a reason oceans amplify atmospheric perturbations. Oceans store roughly 50 times more carbon than the atmosphere. Rapid carbon dioxide pulses dissolve in seawater, acidifying it within decades to centuries. The ocean is, in chemical terms, a buffer that turns into a poison when overwhelmed. The double pulse pattern recurs across multiple extinctions. The Devonian had Kellwasser and Hangenberg. The Ordovician had glacial and deglacial pulses. The End Permian shows multiple Siberian traps phases. Mass extinctions are rarely instantaneous, they are stepwise. Ozone layer destruction also recurs as a secondary kill mechanism. John Marshall has hypothesized it for both the Devonian and the Ordovician. Henk Vischer documented it through malformed pollen for the Permian. Each extinction was followed by ecological reorganization, not just species replacement. Microbial reefs replaced metazoan reefs after the End Permian. Gymnosperm forests replaced lycopod forests after the End Triassic. Mammal radiations replaced dinosaur radiations after the KPG. Each event set the stage for what came next. Recovery timescales with severity. The End Ordovician took 1 to 2 million years. The Late Devonian took 5 million years. The End Permian took 10 million years. The KPG took 3 million years. There's a ratchet effect through deep time. Each extinction permanently eliminated lineages that had survived all previous extinctions. Trilobites survived 9 major extinction events before the End Permian killed them. Eurypterids, the giant sea scorpions, survived everything until the End Permian. Ammonites survived everything until the KPG. Once a lineage is gone, it does not come back. The fossil record itself is biased toward marine invertebrates because they fossilize well. Terrestrial extinction is probably underestimated in the geological record. The extinction statistics we cite are floors, not ceilings. The conceptual leap of this synthesis is that the ocean is not a passive backdrop to extinction. The ocean is frequently the active agent. To understand why the ocean specifically has played this role so many times, you have to understand its chemistry. Ocean chemistry is delicately buffered. Small chemistry shifts cascade through every level of the food web. The carbonate buffer system is the foundation. Carbon dioxide plus water becomes carbonic acid, which dissociates into bicarbonate and a hydrogen ion, which can dissociate further into carbonate and another hydrogen ion. This system normally absorbs atmospheric carbon dioxide, but at high rates of injection, it acidifies the water. Marine acidification is more dangerous than atmospheric perturbation because ocean pH is logarithmic. A 0.3 unit drop doubles hydrogen ion concentration. A 0.6 unit drop, like the End Permian, quadruples it. The aragonite saturation horizon is the depth in the ocean below, which aragonite, a form of calcium carbonate, dissolves rather than forms. As oceans acidify, this horizon rises toward the surface, dissolving the shells of organisms that live in shallower water. The anoxia mechanism is straightforward. Warm water holds less dissolved oxygen than cold water. Climate warming directly reduces ocean oxygen content. This is called ocean deoxygenation. Stratification compounds the problem. Warm surface water does not mix readily with cold, deep water, sealing off oxygen exchange between them. The deep sea becomes anoxic, even without atmospheric oxygen reduction. Eutrophication operates by a different pathway. Nutrient loading triggers algal blooms whose decay consumes oxygen, creating dead zones. The same mechanism that killed the Devonian seas operates today in the Gulf of Mexico, where Mississippi River nutrient runoff creates a seasonal dead zone of approximately 15,000 square kilometers. Hydrogen sulfide poisoning, called euxenia, occurs when oxygen is exhausted. Sulfate-reducing bacteria then produce hydrogen sulfide, which is acutely toxic to most life. Euxenia recurs through the Permian, the Devonian, and possibly the Ordovician. The Strangelove ocean effect is unique to phytoplankton mass mortality. When primary producers die en masse, the entire marine food web collapses from the bottom. It is the only kill mechanism that can affect every trophic level simultaneously. Thermal mass amplifies all of this. Oceans take centuries to millennia to absorb or release heat. Once perturbed, they remain perturbed long after the trigger ends. The deep sea is uniquely vulnerable because its ecosystems have low energy budgets and slow metabolism. Even modest disruption causes mass mortality. The calcium carbonate compensation depth, called the CCD, is the depth at which calcium carbonate dissolves as fast as it falls. The KPG showed this dramatically. Chalk stops appearing in the geological record at the boundary because the CCD rose into water shallow enough that coccolith shells dissolved before they could be buried. Restricted basins are particularly vulnerable. Enclosed seas like the Black Sea today become anoxic faster than open oceans. Many extinction signals come from restricted basin sediments. Marine ecosystems lack the dominant keystone species pattern of terrestrial ecosystems, so extinction propagates differently in the sea than on land. The ocean is fragile in ways the land is not. There is much we still do not know. The exact duration of the Great Oxidation Event remains debated. Was it abrupt or progressive? How many oxygen false starts were there before the rise stuck? The Lomagundi-Getuli excursion's significance is unresolved. Why did oxygen levels crash back down after rising? For the End Ordovician, the ultimate cause of the glaciation itself is contested. Was it weathering-driven carbon dioxide drawdown? Volcanic sulfur dioxide cooling? Some combination? The Late Devonian Kellwasser event's possible asteroid impact connection, proposed by Marina Rakoczynski, remains unconfirmed and contentious. Whether Roemer's gap was a real evolutionary gap or a fossil preservation artifact remains an active debate among paleontologists. For the End Permian, the relative contributions of Siberian traps' direct emissions versus methane hydrate destabilization are not precisely quantified. The question of how fast the End Permian extinction actually was remains open. 60,000 years, 10,000, 1,000. Each estimate implies very different kill mechanisms. Whether the beat-out high structure off northwestern Australia is an End Permian impact crater or a misinterpreted volcanic feature remains contested. The role of the Deccan traps in the KPG extinction is debated. Were they a direct contributor or a stress factor that made the asteroid's effects worse? Why some lineages survived each extinction and others did not is poorly understood. Survivor biology remains one of the great unanswered questions in paleontology. There are also shadow extinctions to consider. The Torsian Oceanic Anoxic Event in the early Jurassic, the Cenomanian-Turonian Oceanic Anoxic Event in the mid-Cretaceous, the Paleocene-Eocene thermal maximum at the start of the Eocene. None reach mass extinction status. What made them less severe than the Big Five? Whether the GOE truly killed most anaerobic life, or just changed where it lived, is impossible to verify without body fossils. Population estimates for ancient microbes are inherently speculative. The ozone destruction hypothesis remains controversial. Direct evidence from malformed pollen is scarce and indirect. And the largest open question of all is whether the next mass extinction is currently underway, and whether it will follow the same patterns as the previous six. Modern ocean science offers an uncomfortable mirror. Current rates of carbon dioxide emissions are roughly 10 times faster than even the End Permian Siberian traps emissions per unit time. Modern ocean acidification has dropped pH approximately 0.1 units since the Industrial Revolution. That number is small compared to past extinctions, but it is accelerating. Projected pH drop by 2100 is between 0.3 and 0.4 units under high emission scenarios. That projection is comparable to the End Triassic acidification. Ocean dead zones are expanding globally. There are now more than 700 documented dead zones. In the 1950s, there were approximately 50. Marine heat waves are becoming more frequent and more severe. They place direct stress on calcifying organisms. Coral reef collapse is well underway. Roughly 50% of coral reefs have been lost since the 1950s. Projected near total loss is the consensus under continued warming. The pattern echoes the Devonian and Triassic reef collapses. Ocean stratification is increasing globally, reducing oxygen exchange and triggering localized anoxia. Plankton populations show concerning trends. Some studies have documented declines in coccolithophore and foraminiferae populations correlated with warming. The biological pump, the process by which carbon is transported from the surface ocean to the deep sea, may be slowing. Mercury, plastics, and persistent organic pollutants are now widespread in deep-sea sediments. These chemical perturbations are without precedent in geological time. None of this means extinction is inevitable. But the trajectory is structurally similar to the events we have just examined. The Intergovernmental Panel on Climate Change and the Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services have explicitly compared current biodiversity loss rates to past mass extinctions. From a geological perspective, the ocean has erased nearly all life 6 times. Whether it does so a 7th time is, for the first time in Earth's history, partly a question of human choice. The ocean is older than any continent. The same water that drowned the Permian still moves through today's oceans. Each of the 6 extinctions left a permanent geochemical signature: sulfide layers, anoxic shales, iridium anomalies, isotope excursions. The ocean keeps records. Many of the geological resources we depend on today are direct products of these extinction events: North African oil from Hirnantian hot shale, coal seams that survived the End Permian coal gap recovery, iron ore from banded iron formations laid down during the Great Oxidation Event. The ocean's vulnerability is also its memory. The same chemistry that makes it fragile makes it a witness. The deep-sea sediments now being drilled by the International Ocean Discovery Program contain records of every ocean perturbation back to the Jurassic. These cores are a continuous archive being read in real time. Each new extinction reset the evolutionary stage. We exist ultimately because the End Permian killed the dominant therapsids, and the End Cretaceous killed the dominant dinosaurs. There is a reflection on scale worth ending on. The Great Oxidation Event took hundreds of millions of years to unfold. The KPG extinction took hours, then weeks, then years to play out. The ocean operates on timescales human minds were not built to grasp. The persistent lesson is this: the ocean is not stable. It looks stable on the timescales of human civilization, only because human civilization has occupied a particularly quiet stretch of geological time. On the deep timescales that matter to the planet, the ocean is a chemistry experiment that has run amok 6 different times. The reframe is uncomfortable. When scientists look at modern ocean trends, they are not comparing them to a stable baseline. They are comparing them to a system that has erased nearly all life 6 times in its history. The ocean has always been the executioner. The asteroid did not kill the ammonites. The volcanism did not kill the trilobites. The forests did not kill the placoderms. The ocean did. The question that haunts modern oceanography, and that has no clean answer, is whether the ocean knows the difference between an asteroid, a volcano, a forest, and us.